Hello, this is Dr. Jacob from Dr. Jacob Lab. Today we have another synthesis of a lecture on organic synthesis of natural product. This time I'll be talking about cocaine analogs. As you know, I already made LSD analog proposal previously. I made methylamycin analogs about a year ago, and our slides have been presented for my work on sulfentanyl and alphentanil about 2 years ago. So this is the next video in that series. I welcome you to this video. So the long-term technology, of course, is to present this technology to startup companies who are interested after all the US patents have been filed. In this presentation, I will be concentrating on novel short synthesis of cocaine analogs. So recently, a novel route to racemic cocaine and analogs was discovered in Dr. Jacob's lab as a concerted project to synthesize several natural products. The following slides will give you a brief, concise details about the synthesis. Let me present you first with the first total synthesis of racemic cocaine in 1901 by Willstatter, as published in Kemper in German. So these are the highlights of his synthesis. Those days, of course, all the new technology, all the new chemical technologies were not available. These are all based on old reactions, but this is a very elegant synthesis, even though it involves many steps. There is a lot of chemistry, old chemistry, which are probably not used much today, but this is how the technology existed those days. The chemical technology those days were limited, but Willstatter did an excellent job of using what he had the knowledge of to make cocaine racemic for the first time. So he starts with cycloheptanone, makes the, as you can see, he makes the oxime with NH2OH, then he cautenizes that and does a Hofmann degradation with silver oxide elimination to take a double bond, and then he adds bromine at the allylic position, bromination, and then he displaces the bromine with dimethylamine to give the allylic amine, and then he proceeds with the next step, putting the next double bond by eliminating, by cautenizing the nitrogen, putting another double bond. And then, of course, he brominates that and puts another double bond by elimination. So you have a cycloheptatriene. Then he adds bromine at the allylic position. So you get HBr added to one of the double bonds. You get the allylic bromide, a diallylic bromide. Then he displaces the bromine with dimethylamine to get the amino compound. Then he brominates, cautenizes, brominates, and then he eliminates with sodium hydroxide, and then he adds HBr to the double bond, and you convert that to the OH with dilute sulfuric acid, and then he oxidizes to give the notropinon, and then he uses sodium and carbonates, make the anion next to the ketone, and carboxyl is carbon dioxide to give the acid salt, and then he protonates the sodium salt with HCl and then makes the ester. So there you have the ester very close to a cocaine, and then all you have to do is benzolate it to give the cocaine mixture of racemic cocaine. So that was the very first synthesis as published in 1901. So here, what's interesting is, in 1901, Richard Willstatter and others reported one of the first synthesis or complete total synthesis of complex natural products. In this seminal work, they started with cycloheptanone, as I mentioned, in 23 steps. So the overall yield is very insignificant, like less than 0.5%, but those days it was a marvelous achievement. Now, Robinson, 10 years later, several years later, Robinson, the Nobel laureate Robinson, came up with a biogenic synthesis of tropinon. He proposed that what is happening in the plant is that you get a kind of like an enzymatic reaction where succinaldehyde and methylamine and acetoacetic acid can combine to give tropinon ester, and then that decarboxylate in situ. That was his Robinson synthesis idea. So the mechanism he proposed was dimethylamine with succinaldehyde forms the imine first, and then you get the imine attacking the aldehyde from a closed system, and then you get cyclization to give the tropinon, carboxylic ester which decarboxylate in situ. Now, in Bottini, in 1971, published in JOC, an elaboration of the Robinson synthesis. Bottini published this work saying that if Robinson synthesis proposal ideas are right, the intermediate has to be going through the cycloheptene dienone. So he showed that if you can make this cycloheptadienone, if you add methylamine, he gets 78% yield just by adding methylamine and methylene chloride. In 5 minutes, you get 78% yield. So that showed that Robinson's proposal going through this intermediate is correct. But however, this creates again, you don't have the ester group of the cocaine. So you get the tropinone. So how he made this is, another article was published in 65 to make the cycloheptadienone. One starts with cycloheptanone and you get the ketal, making the ketal with ethylene glycol by reflexing in toluene phosphoric acid catalyst. You get the ketal and then bromination in ether gives dibromide in very good yield, above 90%. Very clean reaction. Then all you have to do is reflex in sodium hydroxide in flexing methanol. You eliminate the bromine, the bromines, and you get the double bonded ketal. So that goes, I believe, in 75 to 80% yield. And then dilute HCl, room temperature gives regenerates the ketone, dienone. In another, this reaction, the last step also goes very good yield, 90 to 95%. So overall, this is a very good way to make cycloheptadienone from cycloheptanone. So what we came across this idea based on my previous work with methylamycin that selenium can be eliminated to form a double bond at room temperature at 0 degrees or less. 0 degree, between room temperature and 0 degrees and room temperature, if you got a selenium carbon bond can be oxidized to get a double bond. So that idea, I extended it to 2-carboethoxy cycloheptanone. I started with 2-carboxycyclohexanone, heptanone, and then a strong nucleophile can deprotonate both at the C and C6 to give the dianion, and then this dianion is reactive. You can add selenium chloride, phenylselenium chloride to get this typically the dialkylation, and then you can eliminate hydrogen peroxide, oxidize and eliminate to give the 2-carboethoxy group. So this is represented in the next slide how I did this. So in order to make or synthesize the 2-carboethoxy cycloheptanone, I started with dimethyl ester of hexadienoic acid. Hexadienoic acid diester was treated under the Claisen condensation reaction or Dieckmann cyclization condition where strong base potassium tertiary peroxide makes the anion at one of the alpha ester, and then that cyclizes, that attacks the carbonyl group in a Claisen way to get the product. Cycloheptanone carboethoxy ester is formed in nearly 80-85% yield by this reaction. Now once having that, all I did was make the dianion with the lithium diisopropylamide 2 equivalents to generate the dianion here and here, and alkylate with 2 equivalents of phenylselenium chloride to give the diselenate. So here you have the prerequisite for the dienone. This can be oxidized at room temperature or less with hydrogen peroxide in oxygen, in acetone. In excellent yield, like 85 to 90% yield, you get this compound. So there is no need to brominate or dehydrobrominate, make the ketol, it's all in one step. And look what happened, you have the desired cocaine precursor. In other words, whereas Bottini and Robinson made the tropinone without the ester, we can make it all in one pot, starting from this ester, diester, ketoester. So you have this from ketoester, you have this desired cycloheptanone in 2 steps. And then all you have to do is, what Bottini did on the diheptadienone without the ester, the methylamine adds very fast because it's activated by the ketone and by the ester. So here you have a double activation. Methylamine adds first here, and then the nitrogen adds here to get the di addition. So double Michael addition, but much faster than without the ester. With ester, it is slower. Without the ester, it's slower. Now with the ester, this double bond is activated more. You get almost 90 to 95% yield. In 5 minutes, the reaction is over. You can isolate the product, and there you have the desired compound. All you have to do is to make racemic cocaine. You have to reduce the sodium borohydrate. You get a mixture of D and L pair with, you probably definitely get diastereomers. So you have 4 isomers here, because it's 2 diastereomer, 2 diastereomers with the D and L. So you get a mixture, racemic mixture of both diastereomer. So once you react that with phenyl benzoyl chloride, you end up with the cocaine, racemic cocaine. So having made that, the real racemic cocaine, we can make analogs. So instead of methylamine, one can use other primary amines such as benzylamine for one example, gives the analog with the benzyl group here. You can use allylamine, we did, we got excellent yield. Just like methylamine, you got the allyl nitrogen. So the racemic cocaine is replaced, the nitrogen methyl is replaced by allyl, and we also did tertiary primary amine, that also added. We added several amines, primary amines, all of them gave the racemic cocaine. So this is an excellent way to make analogs by changing the structure of the primary amine. So biological activity wise, natural diastereomer, which is the minus or the L isomer, enantiomer, is the active one. So it has high affinity for dopamine, norepinephrine, and serotonin transporters. Strong CNS stimulant and reinforcing effect. So that's why it's addictive. Whereas the other isomer plus enantiomer, much weaker CNS stimulant, but still Blake voltage gated sodium channel. So it has some local anesthetic action, but it's not addictive like the minus. So racemic cocaine, poor CNS stimulant. It's a mixture, so it's a poor CNS stimulant. Local anesthetic activity is retained, but less. So racemic non-natural diastereomer, minimal effect is there. So what you make in the lab with 4 isomers are minimally for your simulation. Cardiovascular effect is there. So it's got anesthetic effect. A mixture containing both racemics will be biologically active but produce less autonomic effect. Much weaker euphoric or stimulant effect, therefore less addictive. So we are ready to transfer technology. A process patent has been filed with the US Department of Commerce. Full experimental details will be available to anyone once the actual patent is filed and approved. So anyone interested in technology transfer can contact me directly at my email at Jacob's Lab or my phone by text or call. So that's the situation now with respect to the cocaine analogs. Till we meet for another video, goodbye.